Hi, everyone. This lecture is the first from chapter 16 on waves. So we're going to talk about, in this chapter, basically the basic mathematical description of waves, a couple of the properties of waves, and then in the next chapter, we'll kind of go a little more specifically into sound waves. Although a lot of the discussion that we have about waves applies to any wave. We could also have waves on the water, waves on a string. We'll talk about waves on a string in a fair amount in this chapter. You can also have electromagnetic waves, which are light. And there are kind of two general classes of waves, transverse and longitudinal. For a transverse wave, the oscillations in the wave are perpendicular to the direction of travel. Right? And so examples of this are water waves, waves on a string, or light waves are also transverse. So let's think about the waves on the ocean, for example. You've got an oscillation, an up and down motion, for example, of a boat. As the wave goes by, it oscillates up and down. But you've also got a wave type of motion and a wave speed of the wave traveling toward the beach. Now the oscillations up and down are perpendicular to that direction of wave motion toward the beach. And so that's typical of a transverse wave. You can also have a longitudinal wave where the oscillations are back and forth in the same direction as the direction of the wave. A typical example of that is a pure sound wave. Right? A sound wave will have the air molecules moving back and forth, oscillating back and forth, but the wave itself is traveling in the same plane as those oscillations. So we want to give a mathematical description of a wave. It's going to look similar to a mass on a spring because there is that oscillation, for example, of the boat up and down. It's going to look like a cosine, right? If we want to describe it, a simple wave. With an angular frequency, a frequency. There's also another variable. So if you take a snapshot in time of the wave, what you'll see is the boat over here on one wave, and then if you go far enough, you'll see a wave at exactly the same height, right? Maybe a wave crest. And they're separated by a distance that we call the wavelength. So I've got a y variable, the height of the wave. I've got an x variable, right, the distance maybe of the wave from the beach, and the distance between two wave crests I call the wavelength. This is called, or the letter used to describe that is the Greek letter lambda, and it's again the distance between the waves. I could pick any 2 points on the wave, right, and go a wavelength. I basically repeated the pattern. So when we want to describe the wave mathematically, we're going to talk about a wave function. I want to know the height of the wave as a function of two variables now, x and t. Not just the time, but also how far away am I from the beach, for example. So I've got, again, two types of motion. The boat oscillating up and down on the wave. Or if I think of a wave on a string, it's a particle in the string that's moving up and down. And then I've got the wave motion of the waves moving toward the beach. You can think of a surfer, right, on top of the wave, riding one of those wave crests toward the beach at the wave speed. So our wave function is going to look like a cosine, and the time dependence is going to look very similar to a mass on a spring. It's got an angular frequency times time. May also have an initial phase angle, but now I've got a dependence on x, and I have another variable k times x in there. Now I've got a plus and minus in front of the omega. I'll talk about the significance of that here in a minute. Again, omega, the angular frequency is just 2 pi times the frequency in hertz, or 2 pi over the period. The k is 2 pi over the wavelength, and it's called the wave number. What it tells me is the number of waves, really, per meter. Right? It's again, I have a 2 pi over lambda here because when x is equal to lambda, I've got 2 pi radians and I've repeated the motion. The cosine will repeat after 2 pi radians. So that's the wave number. Don't get it confused with the spring constant. I'm using K again, but it's not meaning the same thing. So we can talk about the transverse or particle velocity, right? What is the velocity of the boat? Well, it's changing in time, and it's vertical. It's in the y direction. So by transverse velocity, I mean v sub y. It's the y component of velocity. To get that, I can take the derivative with respect to time of my wave function. But this is a 2-variable function now, so really what I'm doing is taking a partial derivative. I'm holding x fixed and taking only the derivative with respect to t. Now, we could also take the partial derivative with respect to x, and that may have some significance that we can talk about later on. But when I take this partial derivative with respect to t, well, I pull out an omega, kind of very similar to the velocity of a mass on a spring. I get omega a sine of kx plus or minus omega t plus phi. But I do want to emphasize, this is not the wave speed. It is the transverse velocity, and it's going to change. It's not a constant, right? It's maximum at equilibrium and 0 at the amplitude of the wave. Well, let's talk about the wave speed now. The wave speed is going to be constant. It's going to be a constant speed moving toward the beach. And what we can do is pick a particular point on the wave, maybe the very top of a wave, the wave crest, and watch it as it moves toward the beach. In this case, we're fixing y. We're looking at a particular height and watching it as it moves horizontally. Since y is fixed, the phase, right, the argument of the cosine is a constant. So I have kx plus or minus omega t plus phi as a constant. Now I can take the derivative with respect to time of this. Well, the phi and the constant are there as constants. They're 0. And I get k dx dt plus or minus omega equals 0. Now dx dt is the wave speed. It's the horizontal speed. So I call that v, even though I guess I should call it v sub x, but people usually don't write it that way. It is the constant wave speed toward the beach. If I add over or subtract over my omega, I can get that v is minus or plus omega over k. Right? The sign changed because I subtracted it over or added it over to the other side. But this tells me the significance of the sign. What it says is that if the sign started out as positive in front of omega, the wave speed is negative, which means it's moving to the left or in the negative x direction. If the sign starts out as a negative in front of omega, the wave speed is positive. It's moving in the right, to the right in the positive x direction. Okay, so that tells me the significance of the sign. I can also write the wave speed not just as omega over k, but in terms of frequency and wavelength. Just plugging in those definitions of omega and k, I find that the wave speed is frequency times the wavelength. V equals f lambda. You could also use that the frequency is 1 over the period and write it as lambda over t, which makes sense, right? It's the distance that one wave travels in one period. Just take distance over time. But this equation is true for any wave. It's a medium wave independent wave speed equation. Any wave, you can calculate the wave speed if you know the frequency and the wavelength. Doesn't matter whether it's a wave on the water, a sound wave, a light wave. This is always true for any wave. Now, the wave speed really, though, is determined by the medium of the wave. What is the wave traveling through? What type of wave is it? For example, a light wave, the wave speed is the speed of light. We'll talk about light waves later on. But let's think about a wave on a string. If you look at the medium is the string. Well, the string has a certain length and a certain mass. One of the things that the wave speed depends on is the mass per unit length. I call that mu. Sometimes people call it the linear mass density of the string. It's the mass per length. It's also going to depend on the tension, how tight you pull the string, right? And the tension is basically a force. I'm not going to prove it here. You can do it either by dimensional analysis a little bit, or actually write out a wave equation, which maybe I'll talk about later. But it turns out the wave speed is the square root of the tension in the string over the mass per unit length. So it depends on the medium. This is a medium dependent equation. It's going to be different, right? If you have a sound wave, you might have a similar equation, but you've got not a mass per length, but maybe a density, a rho, mass per volume of the air or the water, or whatever the medium is that the sound wave is traveling through. So we're going to have medium dependent equations that actually tell us the wave speed, but the wave speed is always related to the frequency and the wavelength through v equals f lambda. So we'll talk more about waves here as we go on, a couple of the properties of waves. And again, in chapter 17, we'll talk more about sound waves.